Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 31 of electrical machines subject. So today we will be discussing about commutation. So before discussing about commutation, I gave you a question as homework. So let's complete that question and then we will discuss about this question about the topic commutation. So we were writing things down that the ampere turns compensated ampere turns per pole was 15,000. Pole arc to pole pitch ratio was 0.68. The interpolar air gap was 1 centimeter. So LGI was equals to 1 centimeter or equals to 10 raised to power minus 2 meter. The flux density under interpole is 0.25. So flux density under interpole is 0.25 Tesla. Given the rated armature current is 850 amperes. IA is 850 amperes. Okay. Determine the number of compensating winding conductors per pole. Number of compensating winding conductors per pole they are asking. So if 12,000, 15,000 is the total ampere turns per pole, how much will the compensating winding produce out of this? So compensating winding will produce 15,000 into the pole pitch upon pole arc upon pole pitch, right? That is 0.68. So this is the number of ampere turns that the compensating windings will produce. So ampere turns of compensating winding ampere turns per pole. Okay, that is equals to what? That is equals to the number of turns in the compensating windings, total number of turns in the compensating winding into the current. What is the current? Current is the armature current into IA because compensating winding is connected in series. Divide by P because it is per pole ampere turns. So what is the armature current? Armature current they have given me as 850 amperes. So from here I can easily find out N compensating. Again, as they are asking me, this will be the overall N compensating, but I need conductors per pole. So N compensating per pole will be what? Turns per pole. So this is basically turns per pole is equals to N compensating upon pole will be equals to 15,000 divided by 850 into 0.68. So 15,000 divided by 850, sorry, 15,000 divided by 850 into 0.68. So this comes out to be 12. So 12 turns per pole. 12 turns per pole. But they have asked me conductors per pole. A single turn will have two conductors. So conductors per pole, conductors per pole will be 2 into 12. So this will be 24. Okay. 24. Okay. So this will be the first answer. This will be the first answer. Now the second answer, the number of turns required on each interpole. What will be the number of turns required on each interpole? So what is the interpole ampere turns? Interpole ampere turns per pole. Okay, it will be basically this 15,000 minus the whatever the compensating winding were producing. So compensating winding was producing this much. So basically 15,000 into 1 minus 0.68. This will be the remaining one that the interpole has to compensate plus the flux density along the q axis that also the interpole has to nullify. So this will be 0.25 bi. I will write here formula. This will be bi into lgi divided by mu naught. It is air gap, right? So this will be 15,000 into 1 minus 0.68. So 4800 plus bi is 0.25 Tesla. Into the length, air gap length is 10 raised to power minus 2. So this will be 10 raised to power minus 2 divided by mu naught. So 4 pi into 10 raised to power minus 7. This is the ampere turns per pole. But what have they asked actually? They have asked the interpole number of turns required in each interpole. So number of turns required in each interpole, this will be what? NC, N interpole, number of turns of interpole into the armature current, because interpole is also connected in series, divided by the pole, right? Number of poles, because this is the overall number of ampere turns, but it should be per pole. Now remember, they are asking each interpole how many number of turns, so I have to ultimately find out n interpole upon p, right? Because I have to find out number of turns per pole. So I will keep n interpole upon p here only. Okay, have they given the number of poles? They actually even have not given the number of poles, and we don't even need the number of poles. Okay, that is great. So this will be equals to 4800 0.25 divided by 4 divided by pi 0.25 divided by 4 into pi into 10 raised to power 5 plus 4800 divided by the current, armature current. What is the armature current? 850 is the armature current, right? So 850 is the armature current. So this will be 7.98. So roughly this will be around 8. So 8 turns per pole will be required for the in case of interpole. Okay, that was the solution. Pretty easy and elegant solution. Same question we have done I think previously as well, right? So let's start with the commutation. So what is commutation? So briefly we already know what happens, right? What is commutation? Commutation is basically the change of current across the coil, right? Whenever this, right, let's say like these are the two conductors and this will move, right, and there is air gap in between. So how do I explain? So this is a circle, right? So this is the circle basically, and this, okay, how do I explain? These two conductors are moving, so there is air gap here, right? There is air gap. So what happens? So this, my middle, this index finger is carrying the, let's say, IC current. This will carry minus IC, because whatever is outgoing, it will be like whatever is outgoing here, it will be incoming here, right? So plus IC minus IC. So suddenly if they flip, right, suddenly this one will come here, this one will come here, what will happen? The current will suddenly change. Due to that change in current, due to the sudden change in current, a voltage will be induced, because this is a coil, this is inductance, and if current is suddenly changed, there will be a voltage induced. That basic principle we will use. That's it. Okay, so if we see before commutation, let's say the coils are in this position. During commutation, what happens? There is no field, right? Basically there is no field. Field is 0 because it is on the q axis during the commutation. After commutation, what happens? The field gets reverses. So you can see from here as well. Previously, let's say this is the coil, this is the voltage of this coil, or this coil, whatever you want to say, or this coil. Let me color it. Let me color it yellow, so that you will be able to understand. So this is the voltage across this coil, right? For this coil. So initially it is about the north pole. Now as the armature will rotate, if you see, as the armature rotates, what will happen? Initially this conductors was in the north pole, now it will come here in the south pole. So the current direction also changes, right? Previously it was, let's say, it was going into the screen, now it is coming out of the screen when it is in the south pole, right? So both the EMF induced also changes, the current direction also changes, right? So same thing I am showing you. So previously it was going here, now the current direction is like this. Induced EMF also direction changes, right? So basically previously the current in the coil was plus IC, because if I assume it to be a DC, right? If I assume it to be DC, previously when it was in the D axis, previously it was plus IC. Now in the Q axis it will be 0, because there will not be any induced EMF, because field is 0, field MMF is 0, hence the induced EMF is 0 and current will be induced EMF upon the resistance, called resistance. As EMF is 0, then the field, then the current is also 0. Then the current in the other axis, south pole, current becomes negative, because you can observe that the sign changes. So this sign here changes. If you see here, the sign changes, right? So current is changing from plus IC to minus IC in the period when there is commutation, just before and after commutation. So something like this arrangement is happening, right? So what is happening through the brush? Through the brush, actually always current current 2 IC will flow. So through the brush, right? Through this brush, always current 2 IC will flow. Okay. Through this brush, the current 2 IC will flow, right? And these are basically my commutator segment, right? If you remember, okay, where is the commutator picture? Okay, that is not here. That is nowhere to be found. We have to go back, go very back. Okay, where is the commutator segment? Commutator segment. Okay, you can skip through this portion. The commutator segment. Okay, where is we have discussed commutator very earlier. Huh? Okay, yeah, this one, right? This is the picture that I was talking about. So I have to go to 300 page. So if you see, basically this is my current waveform. Let me reduce the size. Let me reduce this size. So this is my commutator, right? This is my brushes. So there is air gap in between. So these are my commutator segments. These are my commutator segments. Okay. So what is happening, that this will keep on moving, and slowly the current will keep on reducing. So from this brush, right, 2 IC current will come. So when I am here, this is open circuited, right? Because this is the air gap. This is basically the air gap. So this is basically the air gap. Okay. So what is happening, that through here, then basically through here no current is flowing, because this is open circuited, right? So all of the, like, through here IC current will flow. So I will just draw the diagram. What is happening? So if because brush will always take up 2 IC current. So what is happening over here is that initially, let's assume it is at initially let's assume that all of the current is flowing through this single coin only. So okay, let me change the position. Let me start with this. That will be better, easier for us to understand. Okay, so if I assume it to be somewhere here, okay, it is between the two commutator segments, I mean between the two air gaps, right? So if it is between the two air gaps, like, where will the current flow? So all of this current, right, it is shorted basically. So this 2 IC current will totally flow from here. Okay, 2 IC current will totally flow from here. Okay, now if 2 IC current is flowing, basically what will happen? IC current will flow here and IC current will flow here. Okay, 2 IC current will flow here, IC current will flow here. Okay, so now if this brush changes its location, so now what happens? Let's say if the commutator segments are moving, and we are changing our location. So let's say now if it has reached here, somewhere here. So somewhere here if it has reached, so here the contact is more, so more current will flow through here than here. So this is the air gap basically, right? This is the short circuit path. Okay. So this is basically the commutator, right? This is basically the commutator segment. This is basically the air gap. So this is short circuited, right? So what will happen now? 2IC current will get divided to this 2IC. From here, let's assume that IC current will flow. Sorry, I current will flow, and from here 2IC minus I current will flow. Okay. So ultimately, what is happening? Ultimately, this. So what is the current flowing through these coils? So if here 2IC minus I current is flowing, right? So in this coil still it is in the correct state. This current will be IC only, because this is the coil that is going through commutation. So here the current will reduce. So here the current will be IC minus I, because what will happen is as it is going through commutation, current will slowly reduce, as I was explaining here, right? Current will slowly reduce as it is going through commutation. Okay, slowly current will reduce IC minus I. Here I current is going, here IC minus I current is going, so here I current will be there. So all the other coils always IC current will be there. That is the principle basically. The coil which is undergoing commutation, current will initially start reducing. Okay, so all other coils current will be IC. Okay, all other coils current will be always IC. Okay, so again, if like what is happening again, if I further move, so let me assume this, let's say this is at t equals to 0, this is at t equals to some t1. Okay, now let me move further. If I move it further, so what will happen, this will go backwards more, right? So now what will happen at certain stage, this will be exactly at the middle, right? Air gap will be exactly at the middle, so this will be IC by 2 basically. Sorry, this will be IC here. Sorry, yeah, this will be 2IC is going here, so IC will go here, IC will go there. But am I correct? Yes. So yeah, when it will be exactly in the middle, so from here IC, this path will be equation, this path also will be equation. From here IC current will flow, from here IC current will flow. So from here zero current will flow, no current will flow, right? So that was the state when it has reached Q axis or the MNA. MNA meaning induced EMF is zero, right? Induced EMF is zero. That's the point. That is where our brush should be exactly, right? Collecting the whole current through the other coils. So let's say this is at t equals to t2, and ultimately again when it will reach the right hand side, t equals to, let's assume at tc, what is happening, commutation has totally finished. So what is happening, it has moved up here. Okay, so commutation has totally finished. Now again no current will flow through here, all of the current will flow through the next coil. So now the next coil will go through commutation. So from here the current will be here IC, right? Same current will flow through here. Okay, so what happens that if you see initially across the coil the current was IC on the left hand side. Now after commutation has finished, current is on the right hand side IC, right? So the current direction is changing. So this is basically the graph. This is basically the graph. So if I assume, let's say in tc time, because it is decreasing linearly, the current is going from plus IC to minus IC. So what will be the reactance voltage, right? Voltage developed across the coil or the brushes. So the voltage developed across the brushes will be VL is equals to, I know, L dIL by dt. Correct? VL equals, sorry for the burping. Okay. Okay. As I was saying, VL is equals to L dIL by dt, right? So if VL is equals to L dIL by dt, what will be the reactance voltage? That is what we want to find out. So let me assume that this as the commutation inductance, that is LC. Okay. So I can directly write here the reactance voltage will be what? What is the LC is this? What is the change in current from plus IL to minus IL? So linearly it is decreasing. What is the slope? Basically I have to find out the slope of the current. Slope will be what? This will be simply 2 IC divided by TC. That's it. Simple straight line slope, right? This is the equation for the reactance voltage. Very important equation that will be used in numericals. Okay. Do you have to remember it? No, right? Simple LdIL by dt will do. Right? You don't have to remember anything. Okay, because mostly commutation will be linear only. Okay, now few things I wanted to discuss over here, that this is the commutation time. Okay, TC is the commutation time. Now let me name the time periods. Okay, I will name few time periods. So let me name my TI C. Okay, so let me name few time periods, then I will explain what do I mean by it. So TIC. Okay, so TIC is the time required for reversal of current from plus IC to minus IC. So this is the time TIC. Okay, my eraser is so big. TIC is the time required for reversal of current from plus IC to minus IC. Okay, now let me write this TC. What is TC? TC is the actual commutation time. So TC is the commutation time, which actually basically means commutation time which basically means that the rotor rotates from time that the rotor takes to rotate from north pole to south pole. Okay, time that the rotor takes taken by rotor, okay, to rotate from north pole to south pole. Okay, so this is the case over here. Now let's discuss about few numbers. So if so I can actually take this in the bottom, that will be better. If my, let me use the new color, okay, that we are using. If my TIC is greater than TC, what does it mean? That means the current reversal is taking more time, but the rotor is rotating from going from north pole to south pole earlier. So there is bit of delayed commutation. This phenomenon is known as delayed commutation, in which I am not giving so if, first of all, if the time at which the current reverses from minus I to plus IC or plus IC to minus IC and the commutation time, if both of them are same, let's discuss that case. that if TIC is equals to TC, that basically means there is proper commutation. Proper commutation. Okay, I'm providing enough time, exact same time where the current reverses, right? Okay, now if TIC, the reversal of current is slower and the conductor is rotating faster, that means it is delayed commutation. Commutation is not happening properly in time, so that's why it is known as delayed commutation, and this is what mostly happens. Okay, or also known as under commutation. So this is what mostly happens. Okay, now if the commutation time is lower than TC, this is like this case, this scenario is what mostly happens, practically happens, delayed commutation. And if my current reverses earlier than the rotor goes from north pole to south pole, this phenomenon is known as advanced commutation, or known as over commutation, because I am over commutating it because reversal is happening earlier. So over commutation. Okay, so this is the scenario. Basically this does not happen practically, so practically this does not happen, practically does not happen. Okay, so these are the few things that we have to keep in mind. These are the few terminologies. So why is there, like, why this happens practically, we will understand this. Okay, we will understand this slowly. So this, right, T1 is not the T, it is TIX. Okay, not T1, it is TIC, basically TIC. So like these are the types of commutation that we were discussing. So this will be IC, basically this will be IC, this will be IC, like whatever we have discussed, same thing they are writing over here. Current reverses to early if TIC is less than TC. And okay, let me just remove this, this is not required here. Okay, so yeah, now one more thing, what is IC current? IC current will be the current through every coil. It is equals to what? It will be simply overall armature current by the number of parallel paths. For lap winding it will be IA by A, for wave winding it will be basically IA by 2. That's it. Okay, very simple. These are the things that you have to keep in mind. Now let's like do a bit of theoretical question. Okay, let's discuss about this. So here they are asking that why is achieving proper commutation important in DC machine, and what practical measures can be taken. Okay, so like reason due to improper commutation can happen due to two things. One is delayed commutation. If there is delayed commutation, what will happen is when the current is not zero, then the air gap comes, right? So basically what do I mean? So this mica conductor is here. Where is it? Yeah. So let's say this coil conductor is carrying, let's say, some 0.01 ampere of current, right? So it just comes into the air gap, and at that particular point, I mean, we are at the q axis, right? So what will happen? Current through the coil was 0.1 ampere, but I have came to the air gap, so it is open circuit, so current will instantly go to zero. If it instantly goes to zero, what will happen? Sparking will happen, because a voltage will get induced in the coil, because there is sudden change of current. So that is what they're discussing, that if it is delayed commutation or advanced commutation, what will happen? Sparking or trailing will happen. If it is perfect commutation, then the zero crossing will exactly happen. This zero crossing, right? Zero crossing will exactly happen at the air gap, okay, between the air gap of the commutator segment. So there is no reactance voltage, okay. One more thing, under heavy loading, delayed commutation can cause severe arcing, because of course the current will be huge, right? If current is huge, it is L dit by dt. So rate of change of current also will be huge. Due to that, reactance voltage will be developed that can cause sparking. So as I discussed, so reactance voltage will be developed, that is LC into dit by dt. Another kind of thing is there, that is known as rotational EMF. Due to armature reaction, the magnetic neutral axis shifts, right? So the MNA, previously wherever the MNA was, let me just copy this. So due to armature reaction, we know the MNA shifts, right? So if MNA shifts, then the zero crossing of the current also shifts. This we have discussed, right, previously. So the MNA will now be somewhere here. This will be the MNA. Okay. So MNA has shifted. So instead of this being a dot, this will be a cross, right? So of course the current will reverse here. Current will reverse its direction along the MNA, right? And instead of this being a cross, this will be a dot. Okay. So actually the current is reversing its direction here, but I have already, like physically I have already placed the brushes right here. So what is happening? Again delayed commutation is happening. So my reversal is happening slower. Like reversal is it was supposed to happen here, but it is happening here, right? Current reversal is happening here. So MNA is shifting. So it is an example of delayed commutation. So practically that's why delayed commutation happens. Okay. So yeah. As a result, when the coil is theoretically under the neutral axis, Q axis, it still experiences a magnetic flux. Due to that, and rotational EMF is induced, so current will flow. Yeah, that extra EMF will oppose the current reversal, so that will hamper it. So what do? We use like interpoles, of course, to reduce the armature reaction, so that the MNA should not shift. If the MNA does not shift, then the brush position will be absolutely proper. There will not be any problem. So rotational EMF we can use compensating windings, and reactance voltage we can use interpoles, because in the interpoles here there will be some flux density, right? Flux density by the conductors, that we have done a numerical. So that if I nullify, I will be able to get rid of the reactance voltage. Okay. So yeah, that was basically, these are the main things that we use basically to help. So what are the methods to improve commutation? Mainly there are three kinds of methods. One is, the first one is the resistance commutation. We will see what is that. Next one is the voltage commutation, in which we either shift the brush to the MNA or we use interpoles. Okay. And the third one is the compensating winding, which indirectly helps. This is an indirect way of helping. Okay, not a direct way. Interpoles are the direct way of helping. So we will see one by one. Commutation can be improved by strategies that either enhance the current reversal or minimize the reactance uh, and the rotational EMF that can be induced. So to reduce the time constant, right? Because of course the coil will have some time. Coil will have some time constant. So let equivalently, if I draw the coil will have some RC resistance and some time constant and some inductance, right? LC. So the time constant of this circuit, right? Although we have assumed it to be linear, ideally it is exponential. That also you know, right? If I have a DC voltage source connected, the response will be exponential. But as I'm like approximating few things, that's why we have assumed they're linear. So roughly, I know the time constant of this circuit is RC divided by LC. Okay, sorry, LC divided by RC. Okay, so if I, let's say, because there is problem of delayed commutation, because current reversal happens slowly, so I can make my circuit more faster, because what is the problem is delayed commutation. Delayed commutation. So due to delayed commutation, what is the problem? The problem is reversal is happening slow, right? Current reversal slow. Current reversal is slow. That is what we discussed here, right? In the delayed commutation problem. That current reversal is slow, right? It is taking more time to reverse the current. Time required to reversal of the current. So what I can do, if I decrease the time constant, so things will reach steady state faster. So what will happen is that, where is it? Is that time constant is this, so I want to decrease my tau, so I will increase my RC. So that is what we do, we increase the resistance, right? By increasing the resistance in the coil circuit, tau reduces, which speeds up the current reversal. So we use carbon brushes that has higher contact resistance than copper to aid this increase in resistance. That's why carbon brushes are used. Okay, so carbon has higher contact resistance than copper, aiding resistance commutation. Additional benefits of carbon brushes: it is softer than copper, self lubricating, and it minimizes damage during sparking. So it avoids the damage during sparking. So this is how we can use resistance commutation to further improve our delayed commutation. Okay, next method is voltage commutation. This method aids the commutation by introducing an external voltage that helps in counteracting the reactance voltage. So coil will develop a reactance voltage, so I will give an additional voltage that will counteract this reactance voltage so that there is no sparking. How does sparking happens? Whenever there are two conductors and there is voltage difference between the conductors, let's say plus V minus V, so due to that there will be sparking, right? If this voltage difference is very high, that's why we don't want our reactance voltage to go very high. Okay, so two ways I can do. Either I can shift my brushes here, so that if, let's say if brush is here, right, so this conductor still has some EMF, right? This conductor still has some EMF, and if the brush is there, there will be a reactance voltage. Maybe if I shift my brush in the along the MNA, what will happen? In this axis there is no induced EMF, so there will not be any sparking. So that is the first way with which we can use the brush shifting. But shifting brushes away from the geometrical neutral axis causes partially demagnetizing effect. Okay, like this, right? Although for commutation it is fine, but it can provide partially demagnetizing effect because this is not perpendicular to the field flux lines. Okay, so this was the trade-off basically. So let me, so this you already know, like how it happens. So if brush is shifted in the direction of the generator or opposite to the motor, partially, so if the brush is shifted here, what will happen? If the brush is shifted here, basically now the, yeah, now the flux direction will be somewhat like this, right? So yeah, ultimately what will happen, it will basically, if I shift my brush here, right, what will happen? This flux lines will have two components. One will be along this component, that is the cross magnetizing. One will be along this component, that is the demagnetizing. So it does not matter whether I move it here or here, ultimately it will cause some demagnetization of the field poles. Okay, so basically here what they are discussing, if I rotate my brushes on the direction of the rotation of generator and opposite to the motor, then of course the commutation will improve, right? Because it is along the MNA. Okay, but if I rotate my brush on the opposite direction, of course the commutation will worsen because it is opposite to the direction of the MNA. So commutation will worsen further. Okay, so that is what they're telling me, that it will worsen the commutation. Okay, and like roughly you can see, like if armature reaction is there, it will have some cross magnetizing and demagnetizing effect of the armature reaction, right? That is what we are not discussing here. We had already discussed that previously. Okay, so now let's discuss how interpoles can help. Okay, so interpoles are placed along this GNA, right? So they can provide additional magnetic flux that can nullify the magnetic flux provided by the induced EMF on the conductors. So placed along the interpolar axis, wound in series with the armature, generate a commutating EMF that neutralizes the reactance voltage. So it can generate a field that in turn will generate a induce an EMF on the conductors that will neutralize the reactance voltage and aids the current reversal. Okay, as it neutralizes the reactance voltage, it will aid the current reversal slowly. Okay, that is what a interpoles will do. Okay, interpoles directly improve and sparking is significantly reduced because the reactance voltage is reduced. My reactance voltage VL is reduced. Okay, now let's come to the compensating winding. So compensating winding, we know in turn reduces the armature reaction. So if the armature reaction is reduced, then what happens? The shift of MNA, magnetic neutral axis, will reduce, and if the shifting is lower, of course the commutation will be better because my brushes will be placed along the GNA only. There will not be any problem. So indirectly your compensating winding helps, and it is generally used in large DC machines where armature reaction is very high. So compensating winding will help in reducing the ampere turns per pole for armature reaction. Very good, right? So interpoles are only placed along this region, so they can only help so much. They can only help for the q axis flux, but the interpoles cannot help for this whole throughout ampere turns, right? So for that we might want to use compensating windings. Generally compensating windings is used in large DC machines because there the current is huge. If the current is huge, then the ampere turns per pole due to the armature reaction will be also huge. Okay, so this actually helps indirectly. Because indirectly, why? Because it actually reduces the armature reaction. So if armature reaction reduces, then the of course the MNA shift will reduce, right? So if MNA shift has reduced, then reactance voltage also will be lower. Okay, commutation will work in perfectly. So these are the like comparison. You can go through and read through this. I will not go through this. I will directly solve the questions. Let's solve this first question. A 4 pole lap connected separately excited DC motor is drawing a steady state current of 40 amperes. Okay, so it is drawing a steady state current of 40 amperes at, so IA is 40 amperes at speed equals to 600 rpm. Okay, so what else? A good approximation of for the wave shape of the current in the armature will be, okay. So current in the armature will be somewhat like this, right? It will not always be, basically first of all, current in the armature windings will be IC, I coil will be IA divided by A, right? So as it is lap wounded, IC number of poles is 4. So this will be IA divided by 4, that is 10 amperes. And 10 amperes current will be somewhat like this. So this is the commutation time, basically this small time, right? For rest of the time it is always constant. If I also see here, if you see these coils here, right, throughout this coil current is IC only. If you see here also current is IC, here also IC. Only whenever commutation is happening, then the current is slightly reducing through the coil. That's it. So it will be always constant, that is either IC plus IC or minus IC, depending where the commutator segment is at, and the rest of the time it will be constant. And other than that, here this is the linear curve. So of course this will be option C. Very simple, right? Because current per coil will be 40 by 4 and commutation time is given here. Okay, so in DC machine the armature is always placed on the rotor, unlike in AC machines where it can be located on either the stator or rotor. Okay, so let's, okay, one more thing, let's discuss that what is the time period here. Time period is 25 milliseconds. Can I find out the time period from here? Yes, you can. So they have given you the speed of the armature, right? They have given you the speed of the armature. Have they given me the frequency? Frequency I don't know, but I know this formula, right? I know, so my omega mechanical is equals to 2 pi n by 60, correct? And what is my omega electrical? Omega electrical is p by 2 into omega mechanical, right? And I know that, like, I just want to calculate the time period, basically that's it, right? Just want to calculate the time period. I cannot add in page here. Okay, so okay. Omega e is p by 2 omega n. So So what I can say is that P, right? P is basically 4 by 2. 4 by 2 omega m is what? Omega m is 2 pi n 600 divided by 60. And what is omega e? Omega e is 2 pi f. So 2 pi will get cancelled. This 4 2 will be here. So f, right, will be this 10. F will be basically 20. F is 20 hertz. So what is the time period? Time period will be 1 by 20. Time period will be 1 by 20. So this will be 50 milliseconds. So my time period of the current or whatever, right, frequency will be 50 milliseconds. Isn't that here? So 25 milliseconds, 25 milliseconds. So whole cycle is 50 milliseconds of the current, right? You see now this, right, time is with respect to, like, this is a time, just electrical time, right? So I hope like this also matches. So whatever we have done is absolutely correct, right? Okay, it will not be sinusoidal, it will be like this only. Okay, I hope it is clear. Now let's solve the next question. In DC machine, the armature is always placed on the rotor, unlike AC machines where it can be located either on the stator or rotor. We will learn about AC machines, don't worry. This is primarily because commutation would not be possible otherwise. Armature reaction demagnetizing would not be achievable. No, it is not like that, right? Compensating windings could not be installed in the pole shoes otherwise. DC motors would not be self-starting. So the first one is correct, because if I if the armature is located in the stator, right, then commutation action won't be possible. Because how does commutation happen? So commutation only happens because of this, right? Because it is rotating, ultimately what is happening, this, because this is rotating, the current direction reverses, so is the brush changes from B1 to B2 due to only this rotation action. So armature has to be on the rotor, otherwise I will get a alternating current at the output, right? So if armature, I will write here, if armature is not in rotor, I will get an alternating current, right? Alternating current, basically it means commutation won't happen. Commutation won't happen. Okay, so option A is the correct option here. For achieving sparkless commutation in a DC machine, the armature reaction effect is countered by employing compensating windings and commutating poles, shifting brush axis from the GNA to the MNA, and aligning brush axis with the pole axis, increasing field excitation. No. So they are telling which counteracts the armature reaction. So if I shift my brush from GNA to MNA, what does it solve? It basically solves the problem of commutation, but does it solve the problem of armature reaction? No. So yes, it is correct that I will be able to achieve sparkless commutation, but the armature reaction effect is not countered, right? So here sparkless commutation correct, sparkless commutation correct, but counter armature reaction, no. But this one actually does counter armature reaction by placing compensating winding, which in turn helps in sparkless commutation, right? Last method. So this is, in this case, option A will be the correct answer for this question. Okay, so let's now move on to the next question. When the brushes of a DC shunt generator under load are shifted forward in the direction of rotation, the commutation will improve. Commutation will improve, but the flux will reduce because there is bit of demagnetization, due to which because like there will be saturation, demagnetization, all those things will be there, right? If I rotate the brushes, armature reaction is not reduced. Why? Because if I shift my brushes, what is happening? Armature reaction is still there. Reaction is still there, right? And if armature reaction is still there, there will be bit of demagnetization and cross magnetization. Okay, due to that the terminal voltage will reduce further. Okay, let's now solve the next question. These are all mostly theoretical questions that can come. So in this question it is kind of similar, but here I have a DC motor. If the brushes are shifted from the interpolar axis in the direction of rotation for DC motor, what will happen? So in case of DC motor, right, if the brushes are shifted in the direction of rotation, then I know my MNA actually shifts opposite to the direction of rotation. So I am moving further away from MNA. So basically that means what? That means there is like commutation will further worsen. So commutation will worsen. What will happen to the speed? So I know that armature reaction is there, and due to armature reaction, what is happening? So overall, due to armature reaction, the overall flux per pole will slightly reduce, right? Why? Because armature reaction will have some demagnetizing effect. Due to that the flux will reduce. So I know what is my speed proportional to. Speed is basically proportional to the this voltage, like basically I know what is my eb is equals to V minus IARA, right? So assumption is IARA is not changing, so this is for a motor. So this will be like my speed is basically proportional to the back EMF divided by the flux. This we have already derived. So EB divided by flux, or it is proportional to V minus IARA, that is the numerator is constant, divided by flux. So flux reduces. So if flux reduces, the speed will increase. So speed will increase. So if I shift the brush from the interpolar axis towards the direction of rotation, speed will further increase. Okay. If the armature of a DC shunt motor is rewound using fewer turns of thicker wire, then what will happen? So if I have rewound using thicker wires, so what will happen? If a DC shunt motor, so I am using fewer turns, so N has reduced, number of turns has been reduced. So if number of turns has been reduced, so my flux, right, will reduce, correct? So if flux reduces, what will happen? If flux reduces, that means what will happen? If flux reduces, overall the induced EMF also will reduce, correct? Overall the induced EMF reduces. Okay, so if the induced EMF reduces, what will happen? The current in per coil also will reduce. It is basically EC by R, right? So current also will reduce. So if current reduces, what is my reactance voltage? Reactance voltage is LDIL, L2IC divided by TC. So IC is reducing, so obviously reactance voltage will reduce. So reactance voltage reduces, and if reactance voltage reduces, commutation also will further improve, right? Because there is less chances of sparking. So commutation improves. So reactance voltage reduces, commutation improves. That's it. Okay, that is the intuition that I can give you. Let's now move on to the next question. A 6-pole wound DC machine has an, okay, it is a 6-pole wound machine. It has conductors of 720 and draws a current of 50 ampere from the supply. What is the nature of the flux distribution caused by armature reaction per pole? So nature is triangular, I know already. It will be triangular only. But what will be the peak value? So peak value, we have derived the peak value, right? It was, if you remember, it was basically equals to the number of turns is Z by 2, correct, into the armature current per coil, it is Ia by A, into divided by the pole, right? This is the peak value of the armature flux. This can be asked. So it is 720 divided by 2 into Ia, 50 divided by A, that is 6 into 1 by 6. So this will be uh, yeah, 36. 720 divided by 36, basically 720 divided by 36 into 25. So 500 ampere turns will be the answer. The peak value will be 500 ampere turns. Okay, so option C will be the correct answer in this case. Okay, so let's now discuss the Next question. Why armature reaction becomes more significant at higher loads of DC machine? So basically, why higher loads? Because IA will increase. If IA increases, the flux phi A will increase, and of course that will increase the armature reaction because the main field flux will be affected more. Main field flux will be more affected. Okay, it's a interview kind of question, right? Will be affected. Okay, so same thing, like whatever I've written, same thing is written over here. Okay, another interview question: why is it important to counteract armature reaction in DC machine, particularly at heavy load conditions? So why, like if armature reaction is there, there will be commutation problem, there will be excessive sparking, and of course if MNA is getting shifted, like the brushes can also get damaged. So main field flux, overall like EMF will be lower. Okay, so what are the how do I use? I use ultimately, here they have not mentioned, right? What do you use? So we can use basically what practical issues. Okay, the practical issues they have mentioned here, right? And we use compensating winding and interpoles to basically neglect it. So these are mainly interview questions. In addressing armature reaction, why might an engineer choose interpole over compensating winding? What are the practical benefits? So here you have to just mention like why interpoles are better. So interpoles will be better along the MNA, where they will counteract the q axis flux, right? So it will not disturb the whole main field, they will just counteract the zero crossing points, right? So they are simpler to install, maintain, making them ideal for small to medium size machines. While it is small to medium size machines, the current armature current will anyways be lower, so I will not need the compensating winding, right? Compensating winding is the one that actually totally changes the like opposes the armature ampere turns per pole due to the armature. But as the armature current itself is very low, so my ampere turns per pole, right, due to armature reaction already will be very low, right? For that case, I just don't need compensating winding. What will I do? I will just simply connect the interpoles that will basically fix the axis, right? That will make the GNA and MNA in the same place, right? So interpoles are easy and simple to like install, that's why we use it. On the other hand, compensating windings are more suitable for large machines as they provide broader correction. So if the ampere turns per pole is higher due to armature reaction, then I will use the compensating windings. Okay, yeah, so if simplicity and cost is there, so I will use interpoles. If it is small machine, if it is larger machine, I will use compensating winding. Okay, same thing, it is written that how does armature reaction affect the voltage regulation? Okay, how does, okay, any questions I missed? No, that's it. So how does armature reaction affect voltage regulation in DC generator? Okay, armature reaction. Okay, voltage regulation we will discuss. Basically what happens, if armature reaction is there, the flux generated will be reduced, demagnetizing effect of flux will be there. So if flux reduces, what will happen? Basically my EG will reduce. If EG will reduce, like basically what happens, right? What happens? Voltage regulation. Voltage regulation basically means what is the output voltage as a function of current, right? If I load the machine, what will happen? So basically if IA increases, I know basically my armature reaction will increase. If armature reaction increases, my phi A will increase. If phi A increases, my voltage uh, generated voltage will basically decrease, right? Because my main field flux, resultant flux will reduce, so my EG will reduce. So EG will further go down, right? Or I know my V is equals to EG minus IRA. EG minus IRA. So basically, if my IA is increasing, anyways my V is reducing. Further, it will reduce due to reduction in EG. Okay, due to the armature reaction, right? It will reduce further. So armature reaction distorts the main field in a DC generator, leading to voltage fluctuations, poor regulation under changing load conditions. To counteract this, we use interpoles to neutralize the distortion and compensating windings. Now same question, why are compensating windings necessary in large DC machines and what could go wrong under heavy load if they are not used? So compensating windings are essential for large DC machines because they are the ampere turns per pole due to the armature reaction will be very high. due to armature reaction will be very high. Okay. uh, so this will help. Like, what does compensating winding, you know, just that I'm telling you that why we use it in heavy load, because ampere turns per pole will be very high. Interpoles alone will not be sufficient because they will only fix the q axis flux, right? Armature reaction. So interpoles alone won't be sufficient. Okay. So yeah, that was about it. These were mostly theoretical. You can go through and have a read. You can revise when you will have some like exam, interview or something, right? So that was about all about the armature reaction and all those things. We have finished about armature reaction. So from the next lecture onwards, we will now discuss about the characteristics of the DC generator. Before that, we will discuss about losses in a DC machine. So thank you for watching, and I will see you in the next lecture. Until then, happy learning.